Hi, good day everyone. So this is a continuation of our lecture video on sound and hearing. In our previous video, we discussed about pressure, fluctuation of sound wave function. We also discussed intensity. Now, we will discuss standing sound waves and normal modes. When longitudinal sound waves propagate in a fluid in a pipe, okay, with finite length, say finite length L, so we denote the length of that pipe as L, the waves are reflected from the ends in the same way that transverse waves on a string are reflected at its ends. Now, the superposition of the waves traveling in opposite direction again forms a standing waves. We call this one as standing sound waves. So there are two types of pipe here. We have in this figure shown. This is an open pipe. Open pipe meaning um, both ends are open, and this one is a closed pipe. So closed pipe, it means that uh, one end is closed and then the other end is open. So we call this one as closed pipe, and this one is an open pipe. In a pipe open at both ends, the ends are displacement antinodes. Okay, and the harmonic series contains all integer multiples of the fundamental. In a closed pipe or in a pipe closed at one end, the open end is a displacement antinode and the closed end is a node. And the harmonic series contains only odd integer multiples of the fundamentals. So same with the standing waves in our previous chapter, we can derive the harmonics of an open pipe and a closed pipe. And notice also that we don't see second, fourth, and all even harmonics for a closed pipe. So there is no n equals 2, n equals 4, n equals 6, n that are even numbers. So only odd numbers. Okay, for a closed pipe, the natural frequencies of oscillation form a harmonic series that includes only odd integral multiples of the fundamental frequency. So when I say n equals 1, that's our fundamental frequency f1. When n equals 3, then that will be our third harmonics, okay? Fifth harmonics, seventh harmonics, ninth harmonics, and so on. So there is no even harmonics in a closed pipe, okay? So there's no second harmonics, there's no fourth harmonics, there's no sixth harmonics in a closed pipe. So take note of that. So n is either 1, 3, 5, 7, 9, and so on. So all add numbers for the value of n. Okay. So take note of this. Open pipe is nv over 2l, and for a closed pipe we have nv over 4l. Okay. Okay. So we also have this term. We call this one as beats. Beats are the result of the interference of two sound waves of equal amplitude and slightly different frequencies traveling through the same region. So on the basis of the superposition principle, there will be variation of loudness, and the number of beats per second equals the difference in frequency. So we call this one as beat frequency, and beat frequency is just the difference between the two frequencies of these two waves here. Okay, take note, two waves have the same amplitude, but they have different frequencies, slightly different frequencies. Okay, and the beat frequency, we call this one as f beat, is just equal to the difference of these two frequencies, frequency of this one wave minus the frequency of this second wave, and the resulting wave looks like this one. Okay, we call this one as beat frequencies. Okay, if you add the two sound waves, then the resulting waves will be these blue waves here. Okay, now we will go to our last topic, the Doppler effect. So the Doppler effect refers to the apparent change in the frequency of a sound due to the relative motion of the listener and the source. The mathematical relationship is given by this, where FL is the frequency heard by the listener, and Fs is the frequency emitted by the source. We have to take note that there are two objects here, the listener and the source. So sometimes we draw the listener as L, we draw the source as S, where the source is emitting a sound wave, okay, with some frequency Fs, okay, with some frequency Fs. Now, when they are not moving, okay, when the listener and the source of the sound are not moving, then the frequency heard by the listener is just equal to the frequency emitted by the source. But when these two are moving, okay, say they're moving towards each other, they're moving away from each other, and so on, then the frequency heard by the listener is not equal to the frequency um, emitted by the source. Okay, so we call that one as Doppler effect. And the relationship again is given by this equation, where I call FL as the frequency heard by the listener, okay, where Fs is the frequency emitted by the source, V, take note, is the speed of sound. Okay, speed of sound. So this is around 340 to 350 meters per second. That's the speed of sound. VL is now the speed of the listener. So when your listener is moving, then we have this, we denote the speed of that listener as VL. So speed of the listener, and the Vs is the speed of the source. So when the source is moving, then Vs is the speed of the source. Okay, so when they are not moving, take note, when VL is 0, when Vs is 0, then FL is just equal to Fs. So the frequency heard by the listener is just equal to the frequency emitted by the source. So that is when VL, Vs are 0. Okay, so when the L and S, or when the listener and the source are not moving, then the frequency L is just equal to the frequency emitted by the source. Okay, and this positive minus or minus positive signs indicates the direction of the motion of the listener and the source. So we have to take note of that. So how or when are we going to use positive, negative, negative, and positive in a certain problem? Again, the equation is very simple. FL is just equal to this one, V plus minus VL over V minus plus VL. So it depends upon the problem when we can use plus or minus or plus. Okay, so we will discuss that later. Okay, so what will happen to the wavelengths of the sound waves emitted by the source when the source is moving? The wavelengths are different in front of the source and at the back of the source. In front, it is given by this equation, where V is the speed of sound, S is the speed of the source, and Fs is the frequency emitted by the source. While at the back, the wavelength at the back of the source is equal to this one, V plus Vs over Fs. So notice the wavelength at the front, in front of the source, is much smaller than the wave behind or at the back of the source. It is because your source is moving. So this is an example of Doppler effect using a car horn. So when the source is moving, then we expect that the frequency heard by the listener is different from the frequency emitted by the source. Okay, when it's moving towards, okay, so that's the Doppler effect. The frequency heard by the listener is changing, okay, and it depends upon the motion of the source. So when the source is moving towards the listener, and when the source is moving away from the listener, so that's the frequency heard by the listener. Okay, So again, that's an example of Doppler effect. Now we will go to the sign convention of our equation for Doppler effect. So recall that the equation is given by this expression here. Okay, so when are we going to use plus VL minus VL? When are we going to use plus VS minus VS? Okay, so this is our listener L and this is our source S. Okay, and then for situation 1, when VL is 0, VS is also 0, then FL is just equal to FS. Okay, when they are not moving, then the listener frequency heard by the listener is equal to the frequency emitted by the source. Now, situation 2, when L is moving towards the source, then VL is positive. When the source is not moving, then VS is equal to 0. So the frequency heard by the listener becomes this equation here. Okay, so we will use plus VL when the listener is moving towards the source. Okay, that's situation 2. When situation 3, when the listener is moving away from the source, then VL is a negative number. So therefore, the frequency heard FL is equal to this equation, V minus VL over VFS. Okay, so you have to take note, when L is moving away, then VL is negative. Okay, situation 4, when VL is 0, when the listener is not moving and the source is moving now away from the listener, take note, away from the listener, then VS is plus. Okay, the speed of the source is positive. When the source is moving towards the listener, then VS is minus. Okay, so as you notice, for L, when L is moving towards, then that's positive. When L is moving away from the source, that's negative. But for source, when source is moving away from the listener, then VS is plus or positive. So when S moves towards the listener, then VS is minus. So therefore, FL is equal to this equation. Now when they are moving, when the two are moving, say listener is moving towards the source and source is moving away from the listener, then VL is plus, VS is also positive, so FL is given by this equation. For L moving away from the source, S moving towards the listener, then VL is minus, VS is minus, so frequency is equal to this equation here. When L is moving towards S, S is also moving towards L, then VL is plus, and VS is minus, so FL is equal to this equation here. And for the last situation, we have when the listener is moving away, source is moving away also from the listener, then VL is minus, then VS is positive. So this will be the frequency heard by the listener. So to summarize, when are we going to use positive VL minus VL? Okay, we have to take note. For listener, take note, we will use plus VL when the listener is moving towards the source. Okay, we will use plus VL when L is moving towards the source, minus VL when the listener is moving away from the source. Okay, and for the VS, you can use use minus VS when the source is moving towards the listener. Okay, this is towards the listener, and you can use plus when it is moving, the source is moving away from the listener. Okay, again, plus for VL, this is moving towards the source, minus meaning moving away from the source. Okay, so towards plus, away minus. In the denominator, plus means away from the listener, minus means towards the listener, and that's the sign convention for Doppler effect. Okay, So I think that ends our discussion on sound and hearing. So in my next video, I will give examples on sample problems on sound and hearing. Thank you for listening.